Ganesh, is it visible?
Yes, sir.
Okay, fine.
So today we will proceed with the frequency domain specifications, which is again a very simple thing. There is nothing new, similar to the concept of time domain specifications. So we already know, we already derived in the previous class, the expression for magnitude is given by this, where u is less than 1 and u is also omega by omega n. Similarly, for phase angle, we had the expression of minus 2 zeta u by 1 minus omega square, 1 minus u square. So this is for first case, and we have a second case for u greater than 1. It is 1 minus 180 degree plus tan inverse of 2 zeta u divided by 1 minus u square. So magnitude. Right? So this we already did in the previous class. So the phase angle I wrote in denominator. So if I take it to the numerator, the sign will change. That's the only difference. That's why we got minus now. So now let us derive the expression for mr, omega r, and bandwidth bw. So first is resonant peak mr. The definition is, of course, the maximum value of the gain or maximum value in the gain plot or magnitude plot. And the second one is expression for, the definition for resonant frequency. So it is a frequency at which MR occurs or resonant peak occurs. So let us look into the expression for M. So one key concept we can use is maxima and minima, because we know that resonant peak is the peak value. Also, it occurs at omega r. So we make use of the thing that omega r occurs when m is maximum. When m is maximum. So resonant frequency occurs when m is maximum. So if I want to find maximum m, then I have to go for something differentiation and equating it to 0. That is why the concept of maxima and minima. So that something here is nothing but with respect to u, because u comprises the omega factor. See, for a given system, omega n is always constant. The natural frequency of a system is always constant and it is same. It doesn't vary. So you can say that if omega varies, then only u is going to vary. So without loss of generality or without harming anything to the actual mathematics, we can differentiate this m with respect to u. And later we can make a substitution for u to find the expression for omega. So what we do in the next part is differentiate m with respect to u using the maxima minima concept. So dm by du equals to minus 1. Okay, I'm directly writing the differentiation and equate it to 0. Yeah, of course. So this differentiation goes like this. I will keep the denominator. Yeah, I can differentiate directly here because it's a plus sign. So this differentiation with respect to u becomes 2 into 1 minus u square into 2u plus 4 zeta square into 2u equal to 0. Okay. So denominator, whatever it is, it goes to 0. Yeah, I forgot to write a negative sign here. Sorry for that. So minus u square is minus 2u. That negative sign I have put it here. Fine. So next is simplify. So it is plus 4u cube minus 4u plus 8 zeta square into u. So u is common in all the terms. Take it out and equate it to 0. So I am solving for u here. For what u, m is maximum. That's why I am differentiating. So you will get two solutions for this equation. One is u equal to 0 or u equal to, take these two terms on the other side, then square root of that, which is 1 minus 2 zeta square. So two solutions for u. So obviously we are going to choose a non-zero value. So now the differentiation is done and equated to 0. So using that condition, I can rewrite u equal to ur for this condition. So u equal to ur for this condition. Therefore, omega r equal to omega n into square root of 1 minus 2 zeta square. Okay. So there is a typo here. I is supposed to write 2 here. Okay. So what is next? Next is we need to find the expression for mr. So if you substitute the solved u here, you will get the corresponding magnitude at ur, whatever ur you substitute. So substitute ur or omega r in m to get mr. Okay, so I have written expression of m as it is. Next is I have to make a substitution of u. I am replacing u here, which is nothing but ur, that is square root of 1 minus 2 zeta square. So 2 I have written. So the same 2 will also come here. Okay. So you can now check out u is rewritten as square root of 1 minus 2 zeta square. This u is written as 2 square zeta square, that is 4 zeta square outside, then u is square root of 1 minus 2 zeta square. So now it is to simplify this expression. So the square root will vanish. You have 1 minus 2 zeta square whole square, then 4 zeta square into. Yes, any question? So this and 1 will cancel. Minus 2 zeta square whole square is 4 zeta 4. Then we have 4 zeta square into 1 as 4 zeta square. Then 4 zeta square into 2 zeta square is 8 zeta 4 raised to 1 by 2. The square root I have written as raised to 1 by 2. And finally, we have 4 zeta square minus 4 zeta 4 under the square root. So this is equal to 2 zeta. I will take 4 zeta square as common. This is equal to 2 zeta outside the square root and 1 minus zeta square inside the square root. So this is the expression for mr. So we have both omega r and mr now. Now the next specification is bandwidth. So bandwidth is defined as the frequency or frequency range. Okay, it is also called as range in some other context, at which the magnitude m drops down to 0.707 or 3 dB of 3 dB from its zero frequency value. Zero frequency value. So I'll show you with the graph what is meant by that zero frequency value. So now just understand that it is 0.707 times the magnitude at zero frequency. So that is equal to 0.707 divided by root 2. So it is the frequency at which this much magnitude occurs. Fine, at zero frequency. So solve this. This is self-study, simple steps. And finally, I will write the expression for u square. U square is equal to this one. And if you want u, you will get under the square root. 1 minus 2 zeta square plus or minus square root of 4 zeta 4 minus 4 zeta square plus 2. So this is called bandwidth. So U is actually omega by omega n. Therefore, we have another definition for bandwidth as normalized bandwidth. That is written by replacing U equal to omega by omega n. So that is equal to omega n taken on the other side into the same thing. So this is normalized bandwidth. So plus sign is chosen here because our u or this omega by omega n is always a real positive quantity. So that therefore no negative sign is put. And the last one is cutoff rate. Cutoff rate. So there is no derivation for this cutoff rate. So the general meaning of cutoff rate is it tells about the shape or slope of the magnitude curve. Magnitude curve. Now let us look into the typical frequency response graph. So this is how it looks like, the magnitude plot and the phase plot. 0 degree, minus 10 degree, minus 50 degree on the negative side. Then on the positive side it is plus 50, plus 10 like that. Okay. So this is a 0 hertz point. At that point we have one unit as a magnitude. So 0.707 point is here. So if I draw a line, then this frequency range falls under the bandwidth. And this is omega r and mr. Okay. So we have got the expression for mr, omega r, and bandwidth. Fine. It is little difficult to remember the expression of bandwidth, but if we solve some numericals, it will be easier. So nothing to panic about that. And the derivations are like quite simpler than that of the time domain case. There are only two major derivations, that is omega r and mr, and you need to differentiate the m to get both. So with that, we will solve one simple numerical. A negative feedback control system is characterized by g of s and h of s equal to unity. Okay. Find the values of k and alpha so that mr is equal to 1.04 and omega r equal to 11.55 radians per second. The characteristic equation is given by g of s divided by 1 plus g of s h of s. So we get s square plus alpha s plus k as the characteristic equation. So everything we can do is with the characteristic equation. So comparing with the standard case, 2 zeta omega n is alpha, omega n square is k. Given mr is 1.04, which is 1 divided by 2 zeta square root of 1 minus zeta square. So solving this, you will get zeta, two values. One is 0.6 and other one is 0.8. Okay, so you can try it later. So here we have to select that zeta which is lesser than 0.707 because we will study it later, because for zeta greater than 707 there does not exist any mr. There does not exist any peak. I'll show you in one of the MATLAB simulation. I'll show it later. So for time being, let us see how the gain plot looks like for zeta greater than 0.707 is. There is no peak at all. there's no peak. So if you look at the frequency response of system whose zeta is greater than 0.707, there isn't any peak. So we have to choose 0.6 because MR they have given as MR they have given as 1.04. Next also they have given omega r as 11.55, which means omega n into square root of 1 minus zeta square. So calculate omega n, we get omega n equal to 21.8 radians per second. So these numericals are not as complicated as signal system or field theory. That's why I'm moving a bit faster. We'll revisit the numericals later. So if you solve for omega n and zeta by substituting zeta and omega n here, you will get k and alpha values. K is 475, alpha is 26.2. So now let us calculate the settling time. So if I take a time response or step response for the same system, I still can calculate time domain specification also. So how is that possible? I just need zeta and omega n. So Ts is 4 by zeta omega n. I have zeta, I have omega n. So I can get the settling time. So what I I want to highlight here is, for a given system, both frequency and time domain specifications can be found if you know zeta and omega n. That's it. So next topic is relation between time domain and frequency domain specifications. And again, no derivation, nothing here, just a theoretical understanding. So we know that normalized bandwidth omega equals to say BWN equals to omega n into something. I'll show you one simple relation, remaining you can find out yourself. So B bandwidth, the normalized bandwidth is proportional to n, omega n, whereas the settling time is inversely proportional to omega n. So what I can make out here, what relation I can write about bandwidth and settling time is they are inversely proportional. So if settling time is high, then it means bandwidth is low. Or if bandwidth is high, settling time is low. That is a conclusion. That is one of the relation you can make out. This is only for the understanding purpose. Like you may get some interview question. So also the relation between MR and M is simple. For a stable system, MR should be positive and finite, and so M also. So try to find out one more relation yourself, one more relation, and just try to remember that. Next is again a simple topic, effect of adding a zero and a pole on the open loop transfer function. So how the frequency response changes, how the frequency response will get changed. So this is again additional topic for the purpose of having some knowledge. So I'm going to explain or give only the key point. I'm not going to prove it mathematically because it is out of the syllabus entirely, and the derivation is also very lengthy and laborious. But there is a proof. Whatever the key point I am going to tell here about the effect on the frequency response for adding zero and pole on OLTF, the proof does exist. You can find it in any reference textbook. So let us take a standard second order system, OLTF, that open loop transfer function. So we did omega n squared divided by s into s plus 2 zeta omega n. So now add a 0 to it, like s plus z. Let me call it as s plus z. So what happens after adding the 0 is If z is nearer to origin, and it means very less value, then bandwidth will increase. And therefore settling time will be longer. Oh, just hold on a second. Let me cross verify. Width will decrease or increase.
Sir, if bandwidth increases, settling time should decrease.
Yeah, the settling time should decrease. I think I have to write something else. Let me check my mathematics equation. Okay. Okay. I should have rewritten the sentence. Please make a correction later. If we add a 0, it will increase the bandwidth. Okay, please remember, if we add a 0, it will increase the bandwidth. But if we add a 0 nearer to origin, then settling time will be longer. It means the first sentence is only about adding a 0. Second sentence is about adding a 0 at origin. So please correct it later. So this sentence should be altered, should be rewritten. Sorry for that. So what we'll do is we will add a pole or 0 in the forward path actually. So this is how the forward path addition is represented. Similarly, if we add a pole in the forward path, that is in the denominator, it looks something like this in the forward path. So for this, the consequence is system will become less stable and there is a decrease in the bandwidth. Fine, I will read out the effect once again. Adding a 0 will increase the bandwidth, but adding a 0 at origin or near the origin will increase the settling time. Similarly, adding a pole in the forward path will make the system less stable, okay, and there will be a decrease in the bandwidth. For all these points, there exists a mathematical proof, and it is irrelevant to discuss now. Actually, this point is only for the knowledge purpose. Fine.
Sir,
Yeah.
can you tell that what change you had made over there? Settling time will be longer. That point.
Pardon me. Regarding the first one.
Yes, I remember that point. If z is near to origin, so something change.
Yeah, I will tell it. If you can write down. So after this, remember word you write. If a 0 is added, then bandwidth will increase. Comma.
Yeah.
If the location of the added 0 is nearer to origin, then settling time will be longer. Fine. So these are some key points to remember. And this is again they are correlated with inversely proportionality. So this is also one additional comment you can write about adding a pole. So this is a brief topic on frequency domain analysis. So this chapter told us about that frequency response is something that we are exciting a system with a sinusoidal input and checking its behavior. The reason for going to frequency domain analysis is that we can decompose any signal into different sinusoidal signals Then we can find the response for each sinusoidal, and at the end we can add all the responses to get the complete or total response of the system for a given signal. Fine. So especially while dealing with the noise, one must know the frequency domain behavior of the system, because if you know how it responds to the noise, then you can make out something, you can find out some controller to reduce the effect of noise. Okay, so making something to overcome the effect of noise is something related to sensitivity and all. If you are interested, I have already given slides, you can explore. So with that, we can even take care of the sensitivity of system also. So that is the reason for going to frequency domain behavior. The next topic is polar plot. Polar plot. It's a simple graphical plot. So it's a graphical method to plot open loop frequency response in polar coordinates. Suppose if you have a system, say open loop system g of s into h of s equal to 10 divided by s plus 10, let me take 10 as a common, then I can write it as 1 divided by 1 plus 0.1 s. So substitute s equal to j omega, then we get g of h of j omega 1 divided by 0.1 j omega. So I can write the magnitude as 1 divided by square root of 1 plus 0.1 omega whole square. This should be whole square. Then gh of j omega equal to 1 divided by tan inverse of 0.1 omega. So I'll make a simple table, one for omega, one for magnitude, and one for the phase angle. So I'll choose omega values from 0 to infinity like this. Then I will calculate the magnitude. For omega equal to 0, your magnitude is 1 and phase angle is 0 degrees. Then for omega equal to 2, for omega equal to 2, you will get the magnitude as, okay, I forgot to put a square for 0.1. Okay, 0.1 square and omega square. So when omega is 2, my magnitude is 0.98. Then I am just changing the omega values. So I'll go on doing this. And for infinity, I will simply substitute very high value, which gives me a value nearer to 0. Then calculate the phase angle, tan inverse of 0.1 omega minus tan inverse of 0.1 omega. For different omega, I will get different phase angle. So what I will do is I will plot this on polar coordinates. So this is called as GH plane. It is not S plane now, because I am plotting these values of G and GH, or the loop transfer function. So I will name it as real axis of GH and imaginary axis of GH. No omega is represented in the graph. So we start with the first one. When omega is 0, what is the magnitude? Unity. And what is the phase angle? 0. So you have to locate this point in this plane. So a 0 degree line with the magnitude of unity comes somewhere here. Okay. 0 degree line is of course the positive real axis. Magnitude on that one is somewhere here. So if I go on substituting all this, next is 0.98 but minus 11 degree somewhere here. Then 0.89 minus 26 degree. Then 0.707 with minus 45 degree. Okay. So different omegas, different points. And finally we have at omega equal to infinity, magnitude is 0, angle is minus 90 degree. So magnitude 0 point is nothing but origin, A minus 90-degree line, where we can look at minus 90-degree line? This is minus 90, this is minus 180, this is minus 270. Or this is plus 90, plus 180, plus 270, all are correct. So minus 90-degree line is this one, which tells us that this plot starts from the real positive axis and ends at minus 90-degree axis with a zero magnet. Okay, so this is called polar plot. I have just given introduction. We'll solve few more numericals on polar plot in the next class. Fine. So this is about today's class. Whenever there is a derivation or mathematics, much mathematics, I'll be bit faster because you can watch the videos again and again, and finally you will get to know. And whenever there is a concept, very important concept, I will take more time to make you understand. So I request you to practice the derivations without fail. Don't just look at or listen to the explanation. So in the next class, we will continue with the polar plots. Okay, thank you one and all.